All right, welcome. Today we're going to take a journey right into the heart of modern AI to demystify one of its most powerful ideas, neural networks. We are going to break down how machines are, well, actually learning to think. So let's just dive right in. You know, it all really boils down to this one massive question. What if we could build a machine that doesn't just blindly follow instructions, but actually learns from experience? Something that can spot patterns and make decisions, all based on the amazing 3-pound supercomputer that we all have inside our skulls. That's the mystery we're going to unravel today. So, if you're going to try and build an artificial brain, where do you even start? Well, the pioneers in this field looked at the best blueprint they knew, our own biological brain. This is really the story of how neuroscience kicked off a total revolution in computer science. The connection here is actually pretty direct. I mean, our brains are made up of billions of these tiny little neurons, all interconnected, all receiving, processing, and zapping signals to each other. So artificial neural networks are basically just computational models designed to do the very same thing, creating this massive web of digital neurons that can learn. To really get the difference here, let's think about cooking for a second. Traditional machine learning, well, that's like a cook who has to follow a recipe to the letter. You have to tell it every single step, look for these specific edges, these exact corners. But deep learning? That's more like a creative chef. You just give it the ingredients, the data, and it starts experimenting on its own, learning which combinations and features actually matter to make the perfect dish. It's not following the recipe, it's creating the recipe. Okay, before we get any deeper, let's get on the same page with some of the lingo. First up, you've got the neuron, sometimes called a node. That's the tiny little processor doing the thinking. These neurons get grouped together into layers. Now, the connections between these neurons have what are called weights, which is just a fancy way of saying how strong or important a connection is. And finally, an activation function is basically the gatekeeper that decides if a neuron's signal is important enough to get passed along to the next layer. Those are the fundamental pieces. All right, let's meet the first real character in our story, the perceptron. It's the earliest, simplest form of a neural network, and it's fascinating because it both kicked off the revolution and revealed its first major roadblock. For this, we've got to wind the clock all the way back to 1958. This is when a psychologist of all people named Frank Rosenblatt introduces the perceptron, and it was a totally groundbreaking idea, a single artificial neuron that could actually learn from data. So what is this thing? Well, a perceptron is pretty much the simplest neural network you can possibly build. It's just one neuron that acts as a binary classifier. It takes in some info and makes a simple yes or no call. Is this email spam or not spam? Does this image contain a cat or not a cat? That's the perceptron's whole job. And how it works is beautifully simple, just 4 steps. First, it gets its inputs. Second, it multiplies each of those by a weight to signal how important it is. Third, it just adds them all up. And finally, it looks at that total sum to make a decision, yes or no, fire or don't fire. That's it. Simple, elegant, and for a while there, totally revolutionary. But, and this is a big but, here was the catch. The perceptron was only good at solving problems that were, and this is the key term, linearly separable. What on earth does that mean? It just means you have to be able to draw one single straight line to cleanly separate your 2 groups of data. If you can do that, the perceptron is an absolute genius. But what if you can't? What if the patterns are way more complex, all tangled up with each other? Well, then you're out of luck. The problem becomes, as the source puts it, beyond its computing capability. And this one single limitation, it basically put the entire field of AI into a long winter for years. But then came the breakthrough. The aha moment that took that core idea from the perceptron and just blew it wide open, unlocking the incredible power we see in AI today. And the solution, it turns out, was all about adding depth. The solution was, in hindsight, almost deceptively simple. Don't just use one neuron, use tons of them. And don't just use one layer, stack them up. By adding these hidden layers of neurons between the input and the output, the multi-layer perceptron, or MLP, was born. And this changed absolutely everything. And this is just a brilliant way to see how that depth creates intelligence. Let's take image recognition. The first hidden layer, it might just learn to spot really simple stuff like basic edges and lines. Then the next layer takes that info and learns to combine those edges into more complex shapes, circles, squares. And the layer after that, it combines those shapes to recognize whole objects like faces or cars. See? Each layer learns a more abstract, more complex piece of the puzzle. This multi-layer idea unlocked a whole zoo of different specialized networks. You got convolutional neural networks, CNNs, which are masters of vision, like Face ID on your phone. Then there are recurrent neural networks, RNNs, which are great with sequences like language. That's the magic behind chatbots. And then you have generative adversarial networks, or GANs, which can actually create brand new data, like those hyper-realistic images you see online. Okay, so we've got these powerful, multi-layered networks. Awesome. But how do they actually learn, right? How do they get better and better over time? Well, we're about to pull back the curtain on the learning process itself. It all happens in this simple 4-step loop that just runs over and over and over again. First, in what's called forward propagation, the network takes a look at some data and makes a guess. Second, a loss function measures just how wrong that guess was. Third, a really clever process called backpropagation sends that error signal backward through the whole network, basically telling each and every connection how to adjust itself to do a little better next time. And the fourth step? Repeat. Do it all again, millions of times. Now, the guiding principle for all of this trial and error is a method called gradient descent. The best way to think about it is like you're trying to walk to the bottom of a deep valley, but it's completely foggy. You can't see the bottom, but you can feel which way is downhill right where you're standing. So you just take a small step in the steepest downward direction. That's all the network is doing, constantly trying to take a small step in whatever direction will lead to the smallest possible error. And what's the ultimate goal of that long walk down into the foggy valley? To get to the very bottom, where the error is zero. The network is always striving for a loss of zero, a state where its predictions are absolutely perfect. Now, it never truly gets there, but with every single cycle, it gets just a tiny bit closer. And that brings us to our final and maybe most important takeaway. These incredible networks aren't just programmed with a set of rules. They learn what to do by looking at massive amounts of data. Which leaves us with a really critical question. If these systems learn from our data, what happens when our data is flawed? What happens when it's biased? That's definitely something to think about. Thanks for joining this explainer.
Okay, let's unpack this. We are diving into the architecture behind modern AI, neural networks, and deep learning.
Right. These systems are really the computational heart of so much tech today.
And we're using these academic lecture sources you shared to really shortcut to the core ideas.
Yeah, the goal is to get past the hype, understand how these models actually learn patterns, kind of like a brain does, or at least inspired by it.
So let's jump right in. What makes this field deep? We hear deep learning, machine learning. What's the key difference?
Well, deep learning, or DL, it's a subset of machine learning. The big distinction really is how it handles features.
Features being the important characteristics in the data.
Exactly. In DL, the computer learns the useful patterns and features automatically.
Okay. And this is where that analogy from the sources comes in handy. Traditional machine learning is like using a recipe, right?
Precisely. If you wanted, say, a system to spot a car in a picture, you, the programmer, had to tell it exactly what to look for.
Like, look for 4 circles for wheels, look for this kind of shape. You had to define the features manually.
Yes, manual feature selection. And that gets incredibly complicated very fast for complex problems.
So deep learning is different how? More like the chef?
Kinda, yeah. It's like a chef who learns by trying things out, tasting. You just feed it tons of examples, millions of car pictures, maybe.
And it figures out the recipe itself.
It figures out the important features on its own. It learns, okay, I need to find round things down low and a blocky shape above them, without you ever explicitly coding wheels or car body.
That's a fundamental shift. And the inspiration for this whole structure comes from biology, doesn't it?
It does. Artificial neural networks, the name gives it away. They're computational models inspired by the brain's neural network.
Neurons firing, sending signals?
Pretty much. Artificial neurons get inputs, process them, and pass signals along, mimicking how dendrites receive signals and axons transmit them in biological neurons.
Okay, so to really grasp the power of going deep, we probably need to start simple. Where did it all begin? The first neuron.
The perceptron, that's definitely the place to start. Frank Rosenblatt, way back in 1958.
Wow, okay, so quite a history there.
Oh, yeah. And the perceptron was the simplest possible neural network, really just designed as a binary classifier.
Binary meaning yes or no, black or white.
Exactly. Answering a simple yes-no question like, is this email spam? Or does this patient have the disease?
Got it. But before we hit its big limitation, let's quickly cover the basic parts. These components are in pretty much any neural network, even that simple perceptron, right?
Absolutely. So you have the neuron itself, the basic processing unit, often called a node.
Okay.
These nodes are arranged in layers. You've got the input layer where the raw data comes in.
Like the pixels of an image or maybe sensor readings?
Right. Then there's the output layer where the final prediction comes out. And crucially, in between, you can have hidden layers. That's where a lot of the complex learning happens in deep networks.
And the connections between these neurons have weights.
Yes, weights. Think of a weight as the strength or importance of a connection. A higher weight means the signal from one neuron has more influence on the next.
And there's a bias too.
Yep, a bias term. It's just an extra little adjustment, helps fine-tune the neuron's output, shifts the activation function.
Okay. And speaking of activation functions, what role do they play? They sound important.
They're absolutely critical. The activation function introduces nonlinearity,
Nonlinearity.
meaning it allows the network to model complex, curvy relationships in the data. Without it, even a network with many layers would just be doing a simple linear calculation, like drawing a straight line.
Okay.
Yeah.
So you couldn't model anything complex. The activation function lets it learn curves and corners, essentially.
Exactly. It unlocks the ability to solve really interesting problems.
So back to that 1958 perceptron. It takes inputs, say, your scores on 2 exams,
Applies those weights you mentioned, sums it all up, adds the bias term.
and then uses a simple activation function, like maybe just a step. Is it above this threshold or not?
Right, often a step function back then. And out pops the binary decision. Pass or fail, maybe?
It's a neat little decision maker. And these kinds of classification tasks are everywhere, aren't they?
Oh, constantly. Binary classification like spam filtering, or multi-class classification like recognizing handwritten digits. 0 through 9, that's 10 classes. Or face recognition with potentially thousands of classes.
But the simple perceptron, it didn't take over the world in 1958. It hit a wall. What was that critical limitation?
Its big weakness, its Achilles heel, was that it could only handle problems that were linearly separable.
Linearly separable, meaning you could draw a single straight line to divide the 2 categories.
Exactly. If you plotted your data points, maybe spam emails versus non-spam emails based on certain features, you had to be able to perfectly separate the 2 groups with one straight line. Or in higher dimensions, a flat plane or hyperplane.
And if the groups were mixed up or arranged in a more complex pattern.
Then the perceptron just couldn't do it. It failed. The classic example is the XOR problem. You just can't draw one straight line to solve it.
That's fascinating. Because
Yeah.
didn't Rosenblatt actually prove something about it working?
He did. That's the interesting part. He proved the perceptron convergence theorem.
Okay, what did that guarantee?
It guaranteed that if your data was linearly separable, the perceptron learning algorithm was guaranteed to find the correct separating hyperplane. It would converge to a solution.
So for the simple cases, it was mathematically proven to work.
Yeah.
That must have been huge back then.
It was. A guarantee is a powerful thing in computer science. But the real world isn't always linearly separable, is it?
Not often, no. Real data is messy, complex, nonlinear. So how did AI researchers get past this fundamental limit?
Well, they needed more layers. They needed depth.
Enter the multi-layer perceptron, the MLP.
Exactly. Instead of just one layer of computation, an MLP stacks multiple layers of perceptrons. You have the input layer, the output layer, and one or more hidden layers sandwiched in between.
And suddenly, with multiple layers, you can handle those nonlinear problems.
Yes. Stacking layers allows the network to build up more complex representations of the data.
This is where the deep in deep learning really comes from then.
Yeah.
Having multiple hidden layers.
That's the core idea. A shallow network might just have one hidden layer. It's often faster, uses less power, still very useful for some tasks.
But a deep network has several hidden layers.
Multiple hidden layers, and that depth is what gives it the power to tackle really complex, nonlinear relationships in things like images or language.
Right, let's use that image recognition example again. It really shows how the layers build understanding, doesn't it? Like abstraction.
It's a perfect illustration. So you feed an image, say, a face into a deep network, the first hidden layer. It doesn't see a face at all.
What does it see?
It learns to detect really simple things, like basic edges, little lines, corners, maybe simple color patches, very low-level features.
Okay, just the absolute basics. Then the next layer.
The second hidden layer takes those simple edges and lines from the first layer as its input, and it starts to combine them.
Into what?
Into slightly more complex shapes. Maybe it learns to detect circles or rectangles or simple textures. It's building up complexity.
And then the layers deeper still.
The third, fourth, maybe even deeper layers, they take those shapes and textures and start combining them.
And that's where you start seeing recognizable objects.
Exactly. Those deeper layers might learn to recognize combinations that correspond to an eye or a nose or the outline of a car or the fur pattern of a cat. The network learns these complex concepts piece by piece, layer by abstract layer.
Okay, so the data flows forward through the layers, building up this complex understanding, and eventually the network makes a prediction. That's a cat.
Right, that's the forward propagation step. Input goes in, flows through all the layers, applying weights and biases and activation functions until an output prediction comes out.
But especially when it's first learning, that prediction is probably going to be wrong quite often.
Oh, definitely. Initially, the weights are often random, so the predictions are terrible.
So how does it fix itself? How does it learn from its mistakes? This seems like the magic part.
It's maybe the core engineering marvel, yeah. It's this learning loop, which really involves a few key steps after forward propagation.
Okay, what's step 2?
Step 2 is calculating how bad the mistake was. We use a loss function for this.
A loss function. Sounds like measuring the damage.
Pretty much. It compares the network's prediction, say it predicted dog with 80% confidence, with the actual true label, it was actually a cat. It calculates a single number that represents the error or the loss.
So a single number summarizing how wrong it was. The goal being to make that number as small as possible.
Precisely. Minimize the loss. And that leads to step 3, figuring out how to adjust the network to reduce that loss. That's backpropagation.
Backpropagation. Okay, sounds like going backward.
That's exactly what it is. You take that error signal calculated by the loss function, and you send it backward through the network, layer by layer.
Why backward?
Because backpropagation is a clever way to calculate how much each individual weight and bias in the entire network contributed to the final error.
Wow, okay, so it assigns blame, essentially.
In a mathematical sense, yes. It figures out the gradient of the loss with respect to each parameter. It tells you, if I tweak the specific weight slightly, how much will the overall error change?
And that tells you how to adjust things.
It tells you the direction to adjust each weight and bias to reduce the error most effectively.
Okay, so forward propagation makes a guess. Loss function measures the error. Backpropagation figures out who's responsible. What's the last step?
Step 4 is just training, which really means repeating steps 1, 2, and 3 over and over again.
How many times?
Thousands, millions, even billions of times, depending on the task and the data. Each cycle slightly adjusts the weights and biases based on the backpropagated error.
Until the loss number gets really low and the network starts making accurate predictions.
Until the network is considered trained or converged to a good solution.
And the mathematical engine driving those adjustments during backpropagation, that's gradient descent.
Yes, gradient descent is the optimization algorithm most commonly used. It's sometimes called the method of steepest descent.
Steepest descent, like rolling downhill.
That's a great analogy. Imagine the loss function creates a landscape, like mountains and valleys. The current state of the network corresponds to a point on that landscape. The goal is to find the lowest valley, representing the minimum error.
And gradient descent tells you which way is downhill from your current spot.
Exactly. The gradient tells you the direction of steepest descent, uphill. So to minimize the error, you take a small step in the opposite direction of the gradient vector.
Downhill. Got it. Okay, so that covers the general MLP structure and the learning process. Forward prop, loss, back prop, training via gradient descent. But you mentioned earlier, not all data is the same. The sources talk about a whole zoo of specialized network types.
Yeah, the MLP is kind of the workhorse, the generalist. But for specific kinds of data, we've engineered specialized architectures that work much better.
Like images. MLPs aren't ideal for images, are they?
Not really. An image has spatial structure. Pixels near each other are related. A basic MLP flattens the image, losing that structure. That's why we have convolutional neural networks, or CNNs.
CNNs. What's special about their architecture?
They use these things called filters, or kernels. Think of them as small windows that slide across the image.
Scanning for patterns.
Exactly. Each filter is designed to detect a specific local pattern, maybe a vertical edge, a horizontal line, a certain texture or corner.
So it preserves the spatial information by looking locally first.
Right. And then subsequent layers combine these simple patterns into more complex features. This makes CNNs incredibly effective for image recognition, object detection, medical image analysis. anything with grid-like data.
Okay, so CNNs for spatial data. What about data where the order of things matters, like words in a sentence or stock prices over time?
For sequential data, you need memory. The network needs to remember what came before. That's the job of recurrent neural networks, or RNNs.
How do they have memory? The basic feed-forward network, FNN, just goes input to output, no loops, right?
Correct. FNNs are simple, one-way streets. RNNs have connections that loop back on themselves.
A loop. So the output from one step can influence the next step.
Precisely. This loop allows the RNN to maintain an internal state, or a memory, of previous elements in the sequence. That's crucial for tasks like predicting the next word in a sentence or transcribing speech.
But RNNs have their own issues, don't they? Like forgetting things over long sequences.
They do. It's called the vanishing gradient problem, among other things. They can struggle to remember information from many steps ago. That led to the development of
LSTMs,
Yeah.
long short-term memory networks.
Exactly. LSTMs are a special, more complex type of RNN designed specifically to overcome that long-range dependency problem.
How do they do it?
They have internal memory cells and sophisticated gates, input gates, output gates, forget gates. These gates carefully control what information is stored in the cell, what's forgotten, and what influences the output.
So they can hold on to relevant context for much longer. Makes sense for things like machine translation, where you need the whole sentence context.
Absolutely. Or stock price prediction over long periods.
Okay, two more interesting types mentioned in the sources. First, the one that sounds like a competition, generative adversarial networks, GANs.
Ah, yes. GANs are fascinating. They're different because you actually train two networks simultaneously.
Two networks? Doing what?
You have the generator network, whose job is to create fake data that looks real. Maybe generate realistic-looking faces of people who don't exist.
Okay, the artist or counterfeiter, and the second network.
That's the discriminator. Its job is to look at data, sometimes real, sometimes fake from the generator, and decide, is this real or fake?
Like a detective trying to spot the fake.
Exactly. And they're trained together in competition. The generator gets better at fooling the discriminator, and the discriminator gets better at catching the fakes.
So they push each other to improve.
Yeah.
That's clever.
It leads to incredibly realistic generated content, used for creating art, deepfakes, enhancing image resolution, all sorts of things.
Wild. Okay, last one. Self-organizing maps, or SOMs. What's their niche?
SMMs are a bit different again. They're primarily used for unsupervised learning, mostly for visualization and clustering.
Unsupervised meaning?
Yeah.
No predefined labels.
Right. You give it complex, high-dimensional data with lots and lots of features, and the SOM's job is to map that data down onto a simpler, low-dimensional grid, usually 2D.
Why? What does that achieve?
It arranges the data points on the grid such that similar data points in the original high-dimensional space end up close to each other on the 2D map. It helps humans visualize patterns, clusters, and relationships in complex data sets that would otherwise be impossible to see.
Huh. Okay, a tool for understanding complex data structures.
Essentially, yes.
Wow. Okay, so we've really covered a lot of ground. We went from the perceptron back in '58.
Simple, elegant, but limited to linear problems.
It's failure forcing the need for depth, leading to the multi-layer perceptron.
Which could finally handle nonlinear real-world data.
Then we looked at the learning engine. Forward pass, calculating the loss, and the crucial backpropagation step driven by gradient descent.
The loop that allows these networks to actually learn from experience.
And finally, we touched on this whole zoo of specialized architectures. CNNs for images, RNNs and LSTMs for sequences, GANs for generation, SOMas for visualization.
Each designed to tackle the unique challenges of different data types.
You connect this back to the bigger picture then. The whole story seems to be about overcoming limitations.
I think that's a great way to put it. The journey from the perceptron shows this move from mathematical purity to practical necessity. Understanding why the perceptron failed on nonlinear problems is key.
Because that failure is what drove the invention of deep learning.
Exactly. It highlighted that simple linear models weren't enough. We needed the complexity, the depth, the nonlinearity that MLPs and these specialized networks provide to solve the problems we actually care about solving in the real world.
We started with something that had a mathematical guarantee, the perceptron convergence theorem.
Right. A guarantee of success, but only under very limited, linearly separable conditions.
Which brings us to maybe a final thought for you, the listener, to chew on.
Yeah, something to think about. That perceptron theorem offered this solid mathematical guarantee. As networks got deeper, more complex, tackling these incredibly messy, nonlinear problems, well, those guarantees became much harder, often impossible to come by.
So the question
Is the main goal in deep learning research today still chasing those elusive mathematical guarantees of convergence? Or has the field shifted more towards what works in practice, towards achieving amazing empirical results, better and better approximations, even if we don't have a formal proof that it must converge to the perfect answer? Where does the balance lie now between mathematical certainty and real-world performance? Something to explore.